Alright, let's dive into our first topic and explore the fascinating nature of light. Light is a form of electromagnetic radiation that travels in waves. It has this unique dual nature, as it behaves like both a particle and a wave. This is known as the wave-particle duality. When we talk about light as particles, we refer to them as photons, which are tiny packets of energy that move through space. Now, you might be wondering how this dual nature of light contributes to the formation of a rainbow. Well, the wave property of light is essential for understanding how different colors are formed. You see, light waves have varying wavelengths, and these wavelengths determine the color of the light. For instance, red light has a longer wavelength, while violet light has a shorter wavelength. On the other hand, the particle property of light, or photons, helps us to understand how light interacts with matter. When sunlight encounters raindrops in the atmosphere, the photons within the light interact with the water molecules, causing the light to bend and disperse into its constituent colors. This is the beginning of the process, but eventually leads to the formation of a beautiful rainbow. So, in summary, the unique dual nature of light as both a particle and a wave is a crucial factor in understanding how rainbows are formed. The wave-like properties of light help us to understand the different colors involved, while the particle-like properties allow us to comprehend how light interacts with the raindrops to create this stunning rainbow we see in the sky. Now that we've explored the nature of light, let's move on to our second topic, the visible light spectrum. The visible light spectrum is a small portion of the electromagnetic spectrum that our eyes can detect. It consists of various colors, ranging from red to violet. These colors are often remembered using the acronym ROY-G-B-I-V-I, which stands for red, orange, yellow, green, blue, indigo, and violet. As I mentioned earlier, each color in the visible light spectrum corresponds to a specific wavelength. Red light has the longest wavelength, around 700 nanometers, while violet light has the shortest, around 400 nanometers. The other colors lie in between these two extremes, with their wavelengths decreasing from red to violet. Now, when it comes to rainbows, the varying wavelengths of each color play a crucial role in their appearance. As sunlight passes through raindrops, different wavelengths of light are refracted or bent by different amounts. This is because the speed of light changes as it enters the water droplets, and this change in speed depends on the wavelength of the light. Red light, with its longer wavelength, is refracted the least, while violet light, with its shorter wavelength, is refracted the most. This causes the colors to spread out and form the familiar arc of a rainbow. The order of colors in a rainbow is always the same. Red on the outer edge, followed by the other colors in descending order of their wavelengths, with violet on the inner edge. In summary, the visible light spectrum comprises various colors with different wavelengths. The relationship between these wavelengths and their respective colors is essential in understanding how rainbows are formed, as the refraction of light within raindrops separates the colors based on their wavelengths, creating the beautiful arcs we see in the sky. Let's dive into our third topic, the process of refraction. Refraction is a fascinating phenomenon that occurs when light passes through different materials and changes its speed, causing it to bend. This bending of light is what ultimately leads to the separation of colors in a rainbow. But why does light bend when it passes through different materials? Well, it's because the speed of light changes as it moves from one medium, like air, to another, like water. The change in speed is due to the varying indices of refraction of the materials. The index of refraction is a measure of how much a material slows down light compared to its speed in a vacuum. When sunlight enters a raindrop, it moves from air to water. Since water has a higher index of refraction than air, the speed of light decreases, causing it to bend. This bending of light is more pronounced for shorter wavelengths, like violet, than for longer wavelengths, like red. As a result, the different colors of light are separated and dispersed. As the light exits the raindrop, it moves from water back into air. Once again, the speed of light changes, causing it to bend further. This additional bending further separates the colors,
creating a spectrum of colors that we see as a rainbow.
In essence, the process of refraction is responsible for the formation of a rainbow's colors. As light passes through raindrops and changes its speed, it bends and separates into its constituent colors. This separation of colors, based on their wavelengths, is what gives a rainbow its stunning appearance. Now, let's move on to our fourth topic, the role of raindrops in rainbow formation. Raindrops play a crucial role in creating the breathtaking colors of a rainbow. In fact, without raindrops, we wouldn't be able to see rainbows at all. So how do raindrops manage to create these colorful arcs in the sky? Well, raindrops act like tiny arms dispersing sunlight and bending the different colors of light by varying amounts. As we discussed earlier, this process is known as refraction. When sunlight enters a raindrop, it slows down and bends due to the change in the index of refraction between air and water. As the light exits the raindrop, it speeds up again and bends further. This bending of light causes the colors to spread out, forming a spectrum. The shape and size of raindrops play a significant role in the formation of a rainbow. Raindrops are generally spherical or near spherical in shape, which allows them to act as efficient prisms for dispersing sunlight. Moreover, the size of the raindrops influences the brightness and width of the rainbow. Larger raindrops create brighter and narrower rainbows, while smaller raindrops produce dimmer and wider rainbows. In summary, raindrops are essential in the formation of rainbows, as their shape and size allows them to act as tiny prisms. By dispersing sunlight and bending the different colors of light, raindrops create the stunning and colorful arcs we see in the sky. The beauty of a rainbow truly lies in the power of these tiny droplets of water. We've arrived at our final topic, analyzing the geometry of rainbows. The formation of a rainbow involves some fascinating angles in physics, which ultimately determine the visibility and appearance of this colorful phenomenon. To understand the geometry of a rainbow, we must first consider the path that light takes as it enters and exits a raindrop. When sunlight enters a raindrop, it refracts or bends and reflects off the inner surface of the droplet before refracting again as it exits the raindrop. This entire process is responsible for the dispersion of light and the formation of the colorful arc we see in the sky. The angle at which light exits the raindrop is crucial for the formation of a rainbow. For each color, there's a specific angle called the critical angle at which the light is most intensely refracted. For red light, this angle is about 42 degrees, while for violet light, it's around 40 degrees. The other colors lie in between these two angles. Now, let's consider the observer's position relative to the sun and the raindrops. To see a rainbow, the observer must be standing with their back to the sun, looking towards the raindrops in the sky. The sunlight reflects and refracts within the raindrops, and the observer sees the dispersed colors at the critical angles for each color. The height of the sun in the sky also affects the appearance of the rainbow. When the sun is lower in the sky, the rainbow appears higher and forms a larger arc. Conversely, when the sun is higher in the sky, the rainbow appears lower and forms a smaller arc. In fact, if the sun is too high, the rainbow may be entirely below the horizon and not visible at all. In conclusion, the geometry of rainbows involves a complex interplay of angles and physics, which determine the visibility and appearance of these colorful marvels. The observer's position relative to the sun and the raindrops, as well as the critical angles for each color, all play a vital role in the formation of a stunning rainbow.